Hey, this is for my Chem 1 students. We're going to look at Chapter 6, Section 5. We'll call it Part A. And for molecular structure, today we're going to focus on molecular geometry and molecular polarity. We finished up Chapter 6, Section 2, and we looked at how to draw Lewis structures or Lewis diagrams. We're going to take that a step further now that you can draw those Lewis structures and put a geometry or a shape with each of them. So starting off, Vesper Theory. So Vesper Theory stands for Valence Shell Electron Pair Repulsion Theory. And electrons will pair themselves to orient themselves in order to minimize repulsive forces. You know that electrons are charged the same way, meaning they're negatively charged, and they will orient themselves as far apart as possible. So orient themselves as far apart as possible. And I'm talking about the electrons that are being shared or electrons around our central atom. And again, we are looking at covalently bonded atoms relative to one another. And this would look like possibly one of these structures down here. So the three red circles you see would be three different atoms, and the white cloud structure between them are showing your central atom bonded to two surrounding atoms. So again, Vesper theory, our valence electrons will pair themselves to repel each other. So we're looking at two different types of electron pairs. Bonding pairs, which are going to form your bonds. We're going to show these with a dash when we draw our structure. And then we have lone pairs. So our bonding pairs are also considered to be shared electrons, whereas our lone pairs or non-bonding electrons are called unshared electrons. Bonding pairs, we will use a dash to represent them. Lone pairs, you will see lone pairs as two different dots. And two dots make a dash. So if you're sharing is going to represent at least two electrons. And with these pairs of electrons, our lone pairs, again, we're going to focus on the central atom, repel more strongly than bonding pairs of electrons. So lone pairs affect what we call the bond angle, since they repel more strongly. And if you had, for instance, the one we looked at earlier, something like this, and it looks like that bond angle is 180 degrees, well, if there happens to be a lone pair of electrons on our central atom, they will repel more strongly. They push down on the bonded pairs on each side and reduce that bond angle. So instead of 180 degrees, you'll have something less than 180 degrees. And we'll talk about some of those angles today too. So with you trying to determine your molecular shape, first thing you have to do is draw a Lewis structure. I should have harped on it in section 2. If not, here you go. You have to be able to draw a proper Lewis structure to go forward and attempt to do what we're going to do today. If you do not have a proper Lewis structure, it's not going to matter how many of these shapes you memorize, you would end up applying them wrong. So once you have a proper Lewis structure, we will tally up electron pairs on the central atom. That is very important, on the central atom. So how many lone pairs, how many bonded pairs of electrons are on the central atom? If you run across a double or triple bond, we treat a double bond or a triple bond as one bonded pair. So that will have to be taken into consideration whenever we are counting electron pairs. And then the shape itself is determined by how many bonding and lone pairs of electrons you have. And there are 8 that we're going to go over. I'm going to go over these 8 first, kind of quickly. And then I'm going to want you to go back in and put them all into a chart. I will end up writing the chart at the very end of this particular section. So just know that once we go over all 8, there's a chart that's going to go with it. So the first shape that we have, there are 2 total pair of electrons. Both pair are bonding, and this is a linear molecule, bond angle of 180 degrees, and an example is BeH2. I'm going to draw some quick Lewis structures just so that you can see this. BeH2 looks just like this. There are 4 valence electrons total. All 4 are around your beryllium. Beryllium and hydrogen are both exceptions to the octet rule. Beryllium is filled up with its 4, hydrogen filled up with their 2. That is the proper Lewis structure for BeH2, so the bond angle is 180 degrees, and we call this linear. Now, I will throw in here, even though there is not a bond, if there are only 2 atoms, period, 2 atoms, their shape is also considered linear every single time, but there's no bond angle. For instance, hydrogen bonded to chlorine. There is no bond angle because there is only 1 bond. So if there's only 2 atoms, it has to be linear, but there is no bond angle. So that is our first of our 8. The second one, 3 total molecular pairs, but all 3 are bonding, no lone pairs. There's an example of what it looks like. This is called trigonal planar. Trigonal because it is 3-sided, 3 bonded pair, planar. All of our atoms lay in the same plane, and our bond angle is 120 degrees. So again, if I were to draw out BF3, there's B, there are my 3 Fs. Boron is also an exception to the octet rule, so you will not find any lone pairs around boron, but my 3 fluorines would have theirs around them, but since we are only counting around the central atom, that is 3 bonded pair, no lone pairs on the central atom, trigonal planar, 120 degrees. The next one adds up to 3, but now we start to differentiate. It's 2 bonded pair, 1 lone pair, and this one is called bent. Some books you'll see it called angular, so bent or angular, I would accept either name. And the bond angle is just less than 120. So we put a less than sign at 120 degrees, and the example is sulfur dioxide. If I were to look at sulfur dioxide, SO2, there are 18 total electrons to find a home for. So this is our S, each of our oxygens right here. So that's 2, 4, 6, 8, 10, 12, 14, 16, and for some reason I have a random dot right there, and 18. So again, that big white cloud is really representing a lone pair of electrons. For this one, we would have to take away one of those pairs and form a double bond. So when I look around the central atom, there are 2 bonded pair because we treat the double bond. That's a double bond. That's a bond. We treat the double bond like a single bond. So 2 bonded pairs and then that 1 lone pair give you the bent shape. The next one, 4 total pairs. All 4 are bonding. We're trying to make our shapes look 3-dimensional now. This is tetrahedra. Tetra meaning 4, so 4 bonded pair. And as I look at this, the bond angles are all 109.5 degrees. This has a total of 8 electrons. When I count them up, we've got carbon in the middle, all of our hydrogens right around here, and there you go. You would probably draw it like this, Again, if you still want to draw it four-sided the way we looked at it originally, I am totally good with that. But if you're trying to envision that 109.5 degrees, there's the angle. This one, again, you got to think of this as being three-dimensional coming out at you. All of these angles would be 109.5, reaching down 109.5, but all of them are the same. The next one we have, again, 4 total pair, but this time 3 are bonding, 1 lone pair. This is trigonal pyramidal. So tri means 3, that's our 3 bonded pair, but it is going to take on a pyramid shape. So not all the atoms are in the same plane anymore, and the bond angle is 107. The example is ammonia. Total valence electrons, again, is 8. We have our nitrogen here, our 3 hydrogens, but we have our lone pair right up here on ammonia. So again, if you were drawing this out, you would probably draw it looking, again, four-sided, two-dimensional, and it would look just like that. But again, all of our bond angles, 107. And if you were to go around back, again, this one right around back, that's 107 degrees because you have to think three-dimensional. Next up, again, 4 total pair, but this time 2 bonding and 2 lone pairs. And this one has the same name. I don't know why they gave 2 of them the same names. I know it has to do with the lone pairs, but still. This one is also bent or angular, but we have a reduced bond angle compared to the previous bent one. This one is 104.5, and the example is water. So if you were to draw out the Lewis structure for water, you would have 2 lone pairs up here on your oxygen that are going to even further reduce the bond angle because lone pairs reduce bond angle, and the angle is 104.5. Next up, we have 4 total pair. This time all of them are bonding, which means now we're getting into one of our exceptions to the octet rule, meaning that our central atom is going to expand the octet. This one's name is Trigonal Bipyramidal. Again, the BI means 2. So above, we'll say this equatorial plane right in through here, it's going to look like a pyramid. Below that equatorial plane looks like a pyramid. So it looks like a pyramid above and below your plane. We have 2 bond angles. All of the angles that are right around the equator position that I have highlighted in pink are going to be 120 degrees, but all of the angles that are in the axial position up and down would be 90 degrees. So we do have 2 bond angles associated with each of those. And the example that we're looking at here is PCl5. Again, you draw out your Lewis structure for PCl5. Phosphorus does have 5 valence electrons, but it has expanded to 10 within the structure. So P, all of our Cl's and all of our chlorines would end up having their full octet of electrons, but around phosphorus there are 10 electrons that are being shared. And the last shape that we're going to look at, instead of 5 total pair, is 6 total pair. All 6 are bonding, which means we have to be dealing with another expanded octet. This is called octahedral. Again, you have a pyramid-shaped top and bottom, but that pyramid shape is 4-sided. So it would look 4-sided on top, 4-sided on bottom for a total of 8 sides. That's why you see oct there. But 6 bond pair. All of our angles, either axial or equatorial, are 90 degrees, and the example is SF6. Again, sulfur was one of the ones we talked about that could expand. Sulfur has 6 valence electrons, so again, it expands to double that, which is 12. And as I look, 1, 2, 3, 4, 5, 6, those 6 bonded pair each have 2 electrons. 6 times 2 is 12. There is it in a typical expanded state. Again, phosphorus and sulfur, even though they can expand, they will not always expand. Now, We're going to go ahead before we get into some examples of how you draw these out and do them, and we are going to write our chart out. So let's go ahead and pull up some paper, write us a chart, and get started. Things within our chart. Okay, so I did jump ahead in here, but you're going to go ahead and get your chart set up. Okay, the first one we looked at was called linear. And linear has two bonding pair, no lone pair, around the central atom, and the bond angle was 180 degrees. The next one that we looked at was called trigonal planar. And again, once you have once you're going through with this right here and you know how to draw your Lewis structures, the memorization of shapes is just that. It's memorization. But you have to start with a correct Lewis structure. So this was 3 total pair, no lone pair. And those 3 bonded pair give you a bond angle of 120 degrees. The next one we have was called bent or angular, either one of those. This time again it's 3 total pair, but it's 2 bonding and 1 lone pair. And we said less than 120. It might be somewhere around 118, 119 degrees. The next one was tetrahedral. That's our 4 areas there for tetra. 4 bonding pair, no lone pair. The bond angle was 109.5. After tetrahedral, we had trigonal pyramidal. And we had 4 total pair, but it's 3 bonding, 1 lone pair for 107 degrees. And then after that, another bent or angular. Again, 4 total pair, but this time it was 2 and 2 around the central atom. And our angle was 104.5 degrees. You can see our bond angles, the more that's going on around that central atom, just keep getting squeezed tighter and tighter together. The next one was Trigonal Bipyramidal. Let me spell that right. And this was 5 bonded pair, no lone pair. We had a couple bond angles, 120 and 90. And then the last one was octahedral. 6 bonded pair, no lone pair. All angles were 90 degrees. Now, this is roughly just over, I would say just over half of our shapes. If I were to break this up into sections, so you got your, oh, I don't want to use that. You've got your total of 2 above here. These right here add up to 3. So 3 plus 0 is 3. 2 plus 1 is 3. And then in the next section, those add up to 4. 4 plus 0, 3 plus 1, 2 plus 2. And then you can see a total of 5, a total of 6. Those with a total of 5, there are other shapes there that would be 4, 1, 3, 2, 2, 3. Under 6, there are some other shapes there. Again, these are going to be the main ones that we're going to look at and work with. Again, memorization. Notice that your bond angles, they're getting reduced as you go down through here. You figure out some way. I'm sure there's probably a mnemonic already available online. If you go look it up and trying to remember these shapes, definitely you're going to have to look at bonding pair and lone pair. Once you have your Lewis structure, count up how many bonding and lone pair, and then from memory, you give the shape. This should definitely be in your notes. Let's go work out a couple of examples. So, PF3, there is the Lewis structure for it. Again, by now you should be drawing Lewis structure Again, you should be able to draw Lewis structures pretty good. There's the Lewis structure for PF3. Give it a shot on your paper. Count up all your valence electrons, go through, and see if you can get this Lewis structure. But at this point right here, when we look, we're going to be counting up around the central atom how many bonded pair and lone pairs. I see 3 bonds. I see 1 lone pair. So I go back to my chart. 3 bonding and 1 lone pair goes with trigonal pyramidal, an angle of 107 degrees. And again, if I were looking 3-dimensionally, it would look like that. Another example, carbon dioxide. We've seen this one before, but again, give it a shot on your paper, see if you can get the correct Lewis structure. Looking around the central atom, how many bonding and lone pairs do I have? You count a double bond as 1 bonded pair. So that is 2 bond, no lone pair, linear 180 degrees, and that is what it'll look like. So that covers your molecular shapes. Now we're going to get into molecular polarity. So molecular polarity, we've already been talking about polarity, and you've seen the word dipole. So the direction of a polar bond in a molecule is going to represent the dipole. And again, polar bonds have partial charges. So polar bonds do have partial charges. We use the symbol for the partial positive and for the partial negative. And the symbol that we're going to use for a dipole is something that looks just like this. And the arrow points towards your more electronegative atom. So adding on these right here with HCl, hydrogen is the partial positive because it is less electronegative. So unequal sharing of electrons, chlorine gets its more of its fair share, and that bond really has a dipole associated with it because of the partial charges. And the arrow is pointing towards your more electronegative element. So that is a dipole for your polar bond. When we want to determine molecular polarity of a compound, so we've already looked at polarity for individual bonds. So one bond, is it polar or nonpolar? Well, what if we have a full compound? That's why we've been drawing all these Lewis structures. Now we're going to take these Lewis structures a step further, and we're going to talk about, okay, the compound as a whole, where you have multiple bonds, is the molecule going to be polar or nonpolar? Well, it's going to depend on these dipole moments and its molecular shape. So we do have a few rules that we're going to look at. So to determine the molecular polarity, if it's a non-polar molecule, then your dipole moments are symmetrical and they do not cancel out. So in the case of BF3, you have to think about this as a 3-way tug of war, evenly matched up off of boron. All 3 dipoles are exactly the same because of the partial charges. This is a very symmetrical atom. Now, if I were to add something to this, I think I'll do it here in a moment. For a polar molecule, we're looking for something that's asymmetrical. So either the dipoles don't cancel, in this case the dipoles don't cancel, that looks symmetrical, but the reason why they don't cancel is because we really had that lone pair of electrons on oxygen. That's what reduced this bond angle that we have down here. So with that, if your molecule is considered asymmetrical, then it's going to be polar. Now, throwing in one more thing on you before I kind of sum it all up for you. So, polar molecules, and we're going to stick with this convention for our chapter. We can get into more specifics in Chem 2, but asymmetrical can be lone pairs on your central atom, or the atoms surrounding your central atom do not match up. If all of those would have been chlorine around the carbon, great. It would have been symmetrical, no lone pairs on the central atom, non-polar. But in this case, all of them do not match up, so we're looking at a polar molecule. So, if it is going to be considered non-polar covalent, two things have to happen. Number one, we need a symmetrical Lewis structure, meaning dipoles have to cancel out. In other words, all of your surrounding atoms are identical, and no lone pairs of electrons on your central atom. So if we're going with nonpolar, this is an and situation. And situation here, both of these things have to happen to be considered nonpolar. Now, if we're going to polar covalent, I'm going to take those same two things that you just saw, and it's an or situation. So for polar covalent, you can have an asymmetrical Lewis structure. That's like the CHCl3 we just saw, meaning the atoms around the central atom are not all identical, so your dipoles wouldn't cancel. Or if you have lone pairs on your central atom, then it's considered polar. And it could be one lone pair, two lone pairs, it doesn't matter. So if you have either of these, both of these things might happen, but if you have either one, it's automatically polar covalent. So probably the easiest thing to look at is going to be, do you have lone pairs on your central atom? That's going to be the easiest for what we're doing. Automatically, if you see lone pairs, it's going to be polar. Okay? So that is polarity in a nutshell.